Okay, I'm going to do this problem. It's 2019. I'm going to erase some of my old work here. I started this already, practicing. Okay, so this is 2019. This is the two-block system problem. I have two masses here. I have the force of gravity that's pulling this thing down. I have the two tension forces, which are the same in this case, since this has, it says somewhere here, the pulley has negligible mass and spins with negligible friction. Okay, so we're not concerned about rotation. I also have, these two forces, force of gravity of this guy, normal force of this guy, and then there's no friction, it says, negligible friction. Okay, so now it says, suppose the mass of block A is much greater than the mass of block B. Okay, so this is a huge mass compared to this tiny mass. Okay, before we get anywhere, let's do our shortcut method that we love so much. So I have mass of A, I have mass B. The forces that are pulling it to the right are that force of gravity of this block, this guy. So I'm swinging everything up, swinging this up as if it's in one line. Okay. I have the tensions, which cancel out, so I'm not really concerned about them. I have the force of gravity of A and normal force of A. I'm not concerned about those either because they're not in the direction of the acceleration. Okay, and then I have no friction, so there's nothing here, right? So this is the only force that's affecting this system to make it accelerate. But if this mass was very small, this force is going to be very small because a small mass times gravity is going to give you a small force of gravity, okay? Compared to this block, which has a huge mass. So if I have a really small force pulling down on this, but this thing has such a big mass, what's going to be true about the acceleration? Well, the acceleration is going to be very small. Okay, I feel like if you think about that, like in the physical world, what's happening, the answer is pretty obvious. Follow your gut on that one. Okay, explain your reasoning without deriving or using equations. Let's see. Since mass B is small, the force of gravity of B is relatively small. And since it's pulling a large mass MA, in addition to MB, the acceleration will be small. And then I really want to write the equation net force equals mass times acceleration. If this is big, this is going to be small. I can't use an equation though. So instead, I'm going to write according to Newton's second law, a large mass is indirectly proportional or inversely proportional to acceleration. You can also say it has a big inertia, okay, right? Inertia is a property of mass. The bigger something, the more mass something has, the more inertia it has. That's basically what I just said, I think. Okay, so now suppose the block of A is much less than block B. Estimate the magnitude of the acceleration. Okay, so now, different story. Let's erase this. I'll erase this picture here. Let's see if I can do this. You guys have gotten so much better at my tablet since we've been in quarantine. I guess you'll never know. Well, I guess you will know if you watch these videos. Okay, so here's block B. This is really small. Okay, what's going to be true about the acceleration? Well, this force of gravity is going to cause this thing to accelerate. Really crazy, right? It's as if, let's pretend like this is so small, it's so close to zero. I mean, it might as well not even be there, right? And if it's not even there, that means this thing, there's nothing pulling this string, so there would be no tension. So your block would basically be falling without tension here, which I would say is in free fall. Okay, so estimate the magnitude of acceleration. I would say it's larger than before. I would say acceleration is approximately the same acceleration as gravity. Explain this reasoning without using equations. Since ma is so small, the force of gravity of B is pulling mass B plus mass A, and this is like close to zero. So mass B is accelerating at gravity since mass A isn't providing much of a tension. Much of a tension. Okay, I don't know if that's sufficient. Let's check out the solution. This is it. Okay. Oh, this is just a one-pointer. Oh, for correct answer and justification. So you have to get both to get the point. Nearly equal to G because block B is almost in free fall. I said that. I didn't write it though. A has negligible mass and tension of string is nearly zero. We said that. That's great. Okay. Cool. I'm happy with that. That's great. Moving on. Free body diagrams. Well, luckily, I've been practicing these all year. So, force of gravity of B. Tension. Tension. Force of gravity of A and normal force. I'll say this, they're equal. And these two things are equal. And I'll say this thing, well, let's not talk about acceleration because this is supposed to be arbitrary at this point. Although, if it wasn't accelerating, we would have issues. Anyway, okay. Derive an equation for the acceleration of the blocks after release. Finally, I can use equations. This is great. Okay, so part C says acceleration. So I'm going to go back to this diagram I drew here because I can easily tell what my acceleration is. So net force of the system equals the mass of the system, which is mass A plus mass B times acceleration. So this is Newton's second law. And what are all the forces acting on this? Remember, do not include these forces because they are not in the direction of acceleration. It's only accelerating this direction. So what are all the forces in that line? This thing right here, okay? And the tension forces would also be there. However, they cancel out, so we don't need them. FGB. And we don't write this anymore, so instead of writing FGB, it's okay what we've done so far, but they want me to derive an expression using all the variables they gave me. This is not a variable they gave me, so I need to write mb times g. Okay, I'm solving for acceleration, so acceleration equals mb times g over the sum of the masses. So that's your answer for part C. Okay, so I'll write one arrow there. Consider the scenario from A2 where the mass of block A is much less than the mass of block B. Okay, so again, that acceleration was mb times g over ma plus mb. Okay, so when this thing was much less, I'm going to consider that to be as if it's 0, because it's very small compared to mass B. So now what I have left is mb times g over mb, and guess what cancels out? My mb's. So what am I left with? G. So A equals G. So does it match what I said about it being in free fall? Yep. Okay. So can we just say everything I said is my explanation? Great, thanks. Okay, so this last part of the problem says, while the blocks are accelerating, the tension in the vertical portion of the string is T1. Okay, so that's our original situation. That's this with this negligible mass of a pulley. Okay, so I'm gonna draw this original. Okay, so I have, this is the free body for the original situation, and this is mass 2. This is FG2, and then that tension is T1. And actually I want to make this tension much smaller because this thing is accelerating, and I want to just make it very obvious that this is accelerating. Okay, now it says, next a pulley of negligible mass is replaced by a second pulley whose mass is not negligible. Okay, so I have the situation with the first mass on the table, the pulley. This is not at an angle. Let me just replace that. Okay. Okay, the pulley now has some mass. Okay, which means it has some rotational inertia, I. And I don't really care what that I is at this point. I just know that it's going to cause, this rotational inertia is going to cause the acceleration of this entire system to be smaller, right? Because this thing is kind of preventing this from moving as fast as it could. Okay, so my acceleration of this system is smaller because the pulley has inertia that slows the system down. Actually slows the system's rate of acceleration. Okay, so now that means everything is accelerating not as much. Okay, so this is the new situation. Everything is accelerating not as much. So that means this box specifically is also not accelerating as much. So acceleration is small compared to this arrow, right? FG2 is the same as it was. The mass of that hasn't changed. But how do I make this look smaller? Well, that means my tension force has to be closer to FG2, not as big, because this is still going to accelerate, not as big, but it's got to be closer to FG2 to really make these a little bit balanced. Now, if these were the same, there would be no acceleration. Okay, if these were the same, acceleration would be 0. That's not the case. We're not saying that they are the same. We're saying that the acceleration is so small. So instead of these being the same, this one's just going to be closer to the size of FG2. Okay, so that means T2 must be greater than T1 based on what I just said, because this acceleration is smaller. And that's my reasoning. You guys can put that in words on your own, but conceptually, that's what I am thinking for this one. All right.